Welcome to an exploration of how grain size controls the strength of materials at the nanoscale. When we shrink the grains in a material down to nanometer scales, something remarkable happens to its mechanical properties. Let me start by explaining what grain boundaries are and why they matter for material strength. Most metals and ceramics are polycrystalline, meaning they're made up of many small crystals called grains. Each grain has a different crystal orientation. The interfaces between grains are called grain boundaries, shown here in red. These boundaries are crucial because they act as obstacles to dislocation motion, which is how materials deform plastically. Now let's explore the famous Hall-Petch effect that governs strength in conventional materials. The Hall-Petch equation states that yield strength equals a base strength plus a constant divided by the square root of grain size. Here, sigma y is the yield strength, and sigma 0 represents the intrinsic strength of a material. Ky is the Hall-Petch coefficient specific to each material, and d is the average grain diameter. This graph shows the classic Hall-Petch relationship. As grain size decreases, strength increases following a 1 over square root dependence. But why does this happen? The physics behind this is fascinating. When a material deforms, dislocations move through the crystal lattice but pile up at grain boundaries because the orientation mismatch makes it hard for them to cross. Here you can see dislocations represented by arrows piling up against a grain boundary. The stress concentrates at the boundary. When grains are smaller, there are more grain boundaries per unit volume, creating more obstacles and thus increasing strength. Let's look at some real numbers to make this concrete. Consider pure copper. Let's see what happens as we reduce grain size from 100 micrometers down to 1 micrometer. For copper, the intrinsic strength sigma 0 is approximately 25 megapascals. The Hall-Petch coefficient Ky is approximately 0.11 megapascal meter to the 1/2. Let's calculate. At a grain size of 100 micrometers, the yield strength is 25 plus 0.11 divided by square root of 100 times 10 to the minus 6, which equals approximately 36 megapascals. Now at a grain size of just 1 micrometer, the yield strength jumps to 25 plus 110, which equals 135 megapascals, nearly 4 times stronger. This diagram compares the grain sizes and their corresponding strengths. The smaller grain produces much higher strength. Here's an important question. If smaller is stronger, what happens when we go all the way down to the nanoscale? Can we just keep making materials stronger and stronger by continuously reducing grain size? Let's find out. It turns out there's a surprising twist called the inverse Hall-Petch effect. Below a critical grain size, typically between 10 and 20 nanometers, the strength actually starts to decrease instead of increase. This graph shows the complete picture. Strength increases with decreasing grain size until a peak around 10 to 20 nanometers, then decreases at smaller sizes. Why does this happen? The answer requires us to understand what grain boundaries really are at the atomic level. Let's understand the physics behind this transition from normal to inverse Hall-Petch behavior. When grains are only tens of nanometers across, the grain boundaries themselves become a significant fraction of the total material volume. A typical grain boundary is about 0.5 to 1 nanometer thick, roughly a few atomic layers. For a grain that's only 10 nanometers across, the boundaries can occupy roughly 30% of the total volume. This schematic shows a nanograin where the grain boundary region in blue occupies about 30% of the total volume. Grain boundaries have fundamentally different atomic structure and mechanical properties compared to the ordered crystal interior. At the nanoscale, the way materials deform fundamentally changes. In conventional materials with larger grains, plastic deformation occurs primarily through dislocation motion within the grains. But in nanocrystalline materials, deformation shifts to grain boundary-mediated processes like grain boundary sliding and rotation. On the left, we see dislocation motion in larger grains. On the right, grain boundary sliding dominates in nanograins. Crucially, grain boundary sliding requires less applied stress than generating and moving dislocations when the grains are very small. Let's estimate the critical grain size where the transition occurs. The transition occurs when the grain boundary volume fraction become significant enough to change the dominant deformation mechanism. A rough estimate is that the critical grain size is about 3 to 6 times the grain boundary thickness delta. With a grain boundary thickness of about 0.5 nanometers, the critical grain size is approximately 1.5 to 3 nanometers for the onset of grain boundary-dominated behavior. However, the peak in strength typically occurs at larger grain sizes, around 10 to 20 nanometers, because the transition is gradual. We can also understand this from an energy perspective. Grain boundaries have higher energy than the crystal interior because of the atomic disorder at the interface. The grain boundary energy is typically 0.5 to 1.5 joules per square meter, depending on the material. As grain size decreases, the total grain boundary area per unit volume increases dramatically, raising the total stored energy. The grain boundary area per unit volume is proportional to 1 over the grain size. These high-energy grain boundary regions provide paths for easier deformation compared to the ordered crystal interior. Let's look at a real experimental example with nanocrystalline nickel. Conventional polycrystalline nickel with grain sizes around 10 micrometers has a yield strength of about 100 to 150 megapascals. When processed to have 20 nanometer grains, nanocrystalline nickel reaches a yield strength of about 1,500 megapascals, 10 times stronger. This comparison shows a dramatic strength increase. The nanocrystalline material is an order of magnitude stronger. However, when grain size is reduced further to just 5 nanometers, the strength drops to only 800 megapascals. This clearly demonstrates the inverse Hall-Petch effect. Making grains too small actually reduces strength. This raises an important practical question. If nanocrystalline materials are so strong, why don't we use them everywhere? The answer involves several practical challenges that limit widespread application. First, nanocrystalline materials are thermodynamically unstable. At elevated temperatures, grains grow rapidly, losing the strength advantage. Second, while very strong, nanocrystalline materials often have reduced ductility and fracture toughness, making them brittle. Third, creating materials with controlled nanoscale grain structures is technically difficult and expensive. This illustrates the classic strength-ductility trade-off. High strength often comes at the cost of reduced ductility. Let me give you some analogies to help understand these concepts intuitively. The Hall-Petch effect is like a crowd trying to pass through multiple doorways. More doorways create more bottlenecks, slowing the crowd. People represent dislocations. Doorways represent grain boundaries. More boundaries mean more resistance to flow. The inverse Hall-Petch is like having walls that are mostly doors. Too many doors and the wall itself becomes weak. When grain boundaries dominate the volume, the material starts behaving like boundary material rather than crystal material. Let's look at a more complete mathematical description of the full strength behavior. For grain sizes above the critical size, we use the normal Hall-Petch equation with the 1 over square root dependence. For grain sizes below the critical size, strength decreases, often with a 1 over d dependence in the inverse regime. The crossover between these two regimes occurs around 10 to 20 nanometers for most metallic systems. Let's calculate exactly how much of a nanomaterial is actually grain boundary. Consider a cubic grain of side length d with grain boundaries of thickness delta on all sides. The total volume of the grain plus boundaries is d cubed. The crystalline interior volume is d minus 2 delta, all cubed. The grain boundary volume is the total minus the crystal volume. Let's calculate for a 10 nanometer grain with 0.5 nanometer boundaries. The grain boundary fraction is 1 minus 9 over 10 cubed, which equals 0.271 or about 27%. At just 5 nanometers, the grain boundary fraction jumps to 49%. Nearly half the material is boundary. Despite challenges, nanocrystalline materials have important applications. They're used in protective coatings where extreme hardness is needed, like on cutting tools. In thin film applications, the small volume helps limit grain growth, maintaining nanostructure. They serve as reinforcing phases in composites where specific high-strength regions are beneficial. A typical application, a thin nanocrystalline coating on a tougher substrate, combining hardness with bulk toughness. Current research focuses heavily on stabilizing nanostructures against grain growth using various alloying strategies. Let's summarize the key concepts we've covered. The Hall-Petch effect shows that strength increases as grain size decreases, following a 1/√D relationship. This strengthening mechanism works effectively down to about 10 to 20 nanometers in most metallic materials. Below this critical size, the inverse Hall-Petch effect takes over and strength begins to decrease. The transition occurs because grain boundaries shift from being obstacles to becoming the dominant deformation mechanism themselves. This final graph shows both regimes clearly: the Hall-Petch strengthening at larger sizes and inverse behavior at nanoscale. Understanding both regimes allows material scientists to design optimal nanostructures that maximize strength for specific applications.